Bismillahirrahmanirrahim. Welcome to this brief tutorial on proof techniques. We'll be talking about two kinds of proof techniques. We'll try to understand proof by induction. And we'll try to understand proof by contradiction. So in both of the proof techniques, we'll try to understand through one example in each case that what kind of scenarios, what kind of proof technique needs to be applied. So let's start with a statement whom we want to prove that 1 plus 2 plus 3 up till n is equal to n into n plus 1 over 2. So there are two parts of the statements. One is left hand side, the other one is right hand side. So the technique which we will apply on this example will be proof by induction. There are three major steps which we need to perform while proving something, some logical statement by induction. The first step is known as base case. By base case we mean that what is the smallest possible value of n for which this statement holds true, and that needs to be provided to me that what is n. For example, over here we say n is greater than or equal to, let's say, 1. So this statement will qualify as the base case, and I just need to substitute this base value in the base case, and I need to see whether left hand side and right hand side are equal or not. So for example, we say for n is equal to 1, which is the smallest possible value which n can attain, the left hand side will look like 1, plus up till n will remain 1, and the right hand side will substitute 1 in place of n, and that will become 1 plus 1 is 2, 2 into 1 is 2, over 2 is 1, hence left hand side and right hand side are equal, so our base case holds true. The next important step which we need to take in proving some statement by induction is known as inductive hypothesis. By inductive hypothesis, what we do is that we assume that this given statement will hold true for some unseen given point in between, let's say, k, and that is the kind of hypothesis or assumption which will help us to move ahead, which we'll see in a while. So we assume that the original statement 1 plus 2 plus 3 is true up till k, and we substitute k over here in place of n, so that will look like k into k plus 1 over 2. And on the basis of this assumption, we perform the final step, whom we call inductive step. And over here, we need to show that the given statement holds true up till k plus 1. And we substitute k plus 1 in place of n. This becomes k plus 1 into k plus 2 over 2. So we need to prove this statement based on our previous assumption. And eventually we
the logic is that we can apply the inductive step on assumption. We'll go one step back, one step back, one step back until we reach to the base step. So the intuition is very similar to what we call recursion into gaining. So what we do over here is that we take the left hand side first. We rewrite this whole thing by using our hypothesis. So 1 plus 2 plus 3 up till k plus k1, we are just rewriting it. And this part is something which we know that this is equal to k into k plus 1 over 2 through our hypothesis, and then k plus 1 is getting added. We open up this whole thing, this turns out to be k into k plus 1. If we take this whole 2, so then this k plus 1 will get multiplied with k plus 1. From these two terms, we take k plus 1 as common, and this leads me to k plus 1 into k plus 2 over 2, which is my right hand side. So, and I'm done. So these are the three fundamental steps which we always need to perform while trying to prove something by induction. The next example is slightly different example where we don't have two sides who we need to compare with each other. Rather than it's just one statement that we want to prove that under root 2 is irrational. So the kind of proof strategy which we are trying to apply over here in this scenario is known as proof by contradiction. And when we say contradiction, that means that we start with an assumption, and based on that assumption, we reach at some point which cannot hold true. So when we reach at that point which cannot hold true, then the only flaw in my entire logic will be the assumption. So hence we eventually conclude that the assumption is not correct. Let's see how it goes along. So over here we assume, so this is my original statement who I want to prove. We assume that under root 2 is rational. When we say that some number is rational, we essentially mean that that number can be written in the form of p over q, where p and q both are integers and q is not 0. So that's the fundamental definition of a rational number. So if my assumption is true, then I can write under root 2 as p over q, such that p and q are integers and q is not 0. And an additional part of the definition is that p and q are such kind of integers where they don't have any common factor in between other than 1. So if this statement is true, then what we do is that we take scale on both sides. And it gives me 2 equal to p square over q square. And from this statement, I can write p square as 2q square. And what does this mean? That p square is a multiple of 2, which means that p square is even. If p square is even, that essentially means that p is even. P is even, that would mean that p can be written as 2k. It has 2 as one of the factors. On the other side, how we can write q is that we can write 2q square as p square, and over here we substitute value of p square. 2q square is because p is equal to 2k, so p square will be 4k square, and that will give me q square as 2k square, which essentially means that q square is also even. And if q square is even, then q is even. And if q is even, then q can be written as 2, let's say, j. So p has been written as 2k, q has been written as 2j, which essentially means that both of them have the common factor, which is 2, which is against our assumption, which does not allow p and q to have any common factor. So hence, having the common factor in both of in between p and q, we are reaching to a point which we call contradiction. Contradiction is with our assumption, and the assumption was that under root 2 is rational. So hence, if under root 2 is rational, then p and q must have to have something in common, which is not allowed in the definition of rational numbers. So hence, my assumption is incorrect, and if my assumption is incorrect, then inverse of that statement would be true, which is that under root 2 is irrational. Thank you very much.